Hello, Year 11. Today's lesson is going to be a bit different because we're supposed to be doing a required practical and we can't do that because we're at home. So there's the lesson folder. We're learning about Hooke's law. Inside the lesson folder, these two links are to, the top one's to a YouTube link, the free science lesson guy. If you can't understand what I'm getting at, or maybe I don't give you quite enough, you can go watch him. And the simulation that I use in the video, which I'm going to move on to next, is here. There'll be a third one, which will be this video once I finish recording. Now, I'm just going to go straight in and start with the simulation. You should remember something that looks a bit like this. We did an experiment before where we had a clamp stand and we put a spring on it. We measured the spring at the start, so this is the right one here, sorry, the left one. We measured the spring at the start, then we put some masses on so that we had a force pulling the spring down, and we measured the distance that the spring had moved. We call this the extension. Then we put more force on, and then we measured the extension there. Okay, and eventually we come up with this equation at the top, but we'll leave that for now. So here I've got a spring attached to a wall, and I've got a little hand here that grabs it. At the moment this spring is left alone, it's not being touched, so this is its natural length. The spring is naturally this size. Now what you would do before you put any force, or sorry, before you applied any force to this spring, you would measure the length of the spring. So you could measure this, maybe it's 10 centimeters long. Then what you do is you apply a force, so you grab the spring and you pull. So if you look at this green arrow, that green arrow shows you the extension of the spring. Okay, so far I have moved that spring this distance, so maybe it is now at 12 centimeters in length in total. But we started with 10 centimeters and we've extended it 2 centimeters. Okay, so then you can keep pulling, and this green arrow shows you how far I have stretched that string. Okay, you can do the same the other way. You can compress a string, just like in your car suspension. You compress the string, but the extension would be that direction. Okay. Let's put it back to 0. I'm now going to add on the force, the spring force. Okay, this will be a blue arrow. So as I pull this spring to the right, okay, it will extend with the green arrow, but the blue arrow shows you the force that the spring is exerting on this hand. And that makes sense, right? Because if you were pulling this spring, you would feel it. You would feel the spring pulling against you. So if this was your hand and you were trying to stretch this spring because you were going to flick it at someone, you would feel the spring pulling against you that direction. Okay, and the more you pull, the greater the spring force is. So let's go back down to 0. If you were to squash a spring, again, like on a car suspension or on bike suspension, the same thing happens. If I squash the spring, it tries to push me in the opposite direction. Okay. Now let's look at the graph. Here we've got displacement, which was the green arrow before, which is here, the green arrow. Okay, you can see I am extending it by 3.5 centimeters there, up to 1 whole meter. Now, when we do this experiment, what we would do is we would go, say, 5 centimeters. We'd put a mass on, sorry, and then it would stretch a little bit. We would record it. We put another mass on. It would stretch a little bit. We would record that. We would record the extension. We would keep doing the same thing, and eventually, okay, you would see those little dots that I just put it on here. You would plot this graph. Now, this graph is, in maths, what you would call directly proportional. You see that this is a straight line that goes through the origin. So where these two axes cross, that is the origin. You've got a straight line that goes through that origin. Now, what this is saying is, as you pull on here, so I'll put the values back on again, as you pull this spring, the force of the spring increases, but it increases at the same rate. So let's say I went to try and get it 0.5 meters. If I was to double this, the force should double. So if I take it up to 1 meter, this force should read 200 newtons, and it does. Okay, because this is directly proportional. If something is directly proportional, if you double one thing, so in this case if I double the displacement, the force will double. If I half the displacement, the force will half. If I divide the displacement by 10, so will this. So if I make this 0.1 meters, this should be 20 newtons. So let's have a test. 3, 2, 1, 8. There you go, you see. So if I, again, do it the other way around, if I multiply this by 10, this should multiply by 10. So from back up to 1 meter, that should be 200, and it does. Now, when we do this experiment, we plot this graph, okay, force and extension, and we come up with the equation F equals K times E. I won't get too mathsy with this because you should be able to relate this back to the equation for a line, as in y equals mx plus c, but we won't do that. Now, what happens is, this is your force, which you know, so let me write this in green. You know that this is your force, because that's a standard symbol. This E stands for extension, as in how far do you stretch that spring, and the K, which is a new one, that is your spring constant. And essentially what the K means in real life terms is how strong is your spring. So it's the spring strength. So if you had a bigger K, you would have a stronger spring. Now, at some point, so let's say, these numbers don't really matter, all you need to know at the moment is if you increase the force of this spring, the spring is going to get longer, right? And it happens, it's a straight line that goes to the origin. But there'll be a point, so let me just put a dot here. There'll be a point, and then what will happen is the graph will do like that, it will curve. Now, that point there, where this line stops being straight, has a special name. So I'm going to call this P for now, and underneath where I've got more room, I'm going to write what that is. So P equals the limit of proportionality. Now, because this graph is directly proportional, yeah, straight line, that P there, that dot, is where it stops being directly proportional. That is why we call it the limit of proportionality. What does that mean, like in real terms? Well, if you had a spring that looked like this, okay, after it's gone past P, if you got your spring back, it's going to look like this. Okay, you notice that the spring has changed in length, or the spring has deformed. Oh, that's a very thick line. Let's change that back. Okay, so this is now, this is deformed or changed size. Right? Your spring is essentially broken. So if you were given a question and it said, how could you tell, let's say you were given this graph, let me start that again, let's say you were given this graph here. After this experiment has finished, what could you say about the spring? Well, from this graph you know that this spring has gone past its limit of proportionality, so it must be deformed or broken. You would then say, something like the spring has not gone back to its original size, or the spring has been deformed. Now, that is really all we need to know about this for now. When we get back into school, we'll practice a bit more of plotting the graph, taking the results, and stuff like that. But as long as you know this experiment and it kind of jogs your memory a little bit, as long as you know this equation, which is quite important, and maybe we should focus on remembering one thing, and that if the graph looks like this, you've gone past your limit of proportionality. So in order of importance, let's do that. Let's say 1, you need to know what P is. Okay. 2, we'll do the graph because we need graphing practice, but that's hard to do from home. And 3, again, that's just a memory thing. Practice with this equation we will do when we are at another time. For now, we just need to learn the theory. So they're the 3 things. 1, you need to know what the limit of proportionality is and what it means. 2, this graph, okay, and 3, this equation.